Hi. Yesterday we did concepts of electric potential. Glad to see we got everybody nicely separated there. Today we're going to do equations, and we'll try to tie the concepts and the equations together. And to do this, I want to review a little bit, and then I want to talk about specific problems that are found in your book. So, concepts. First of all, electric potential measures energy per unit charge. In other words, 1 volt is equal to 1 joule per coulomb. Okay. And we think of electric potential as being like or analogous to the height that an object or that a cliff would have.
Mr. Cagle?
Uh-huh.
Sorry, really fast before I forget. But it's about homework. Can I just ask a really fast question?
Yeah.
Last week when we were off Thursday and Friday, you still had homework on lunch. We were still supposed to do those, right? Or
so do the Thursdays but not the Fridays.
Okay.
Oh, really? I think that was the answer I gave to somebody else that asked about that. Did you ask about that?
Well, you said not to do Thursdays.
Yeah,
Don't do Thursdays and Fridays. That's fine. There's enough to keep you off the streets now. So we had for gravity, we had delta U is equal to mg delta H, right? And for electrical, we're going to have delta U is equal to Q times E times delta X. And so the analogy is between the gravitational field and distance, or gravitational field times distance is gravitational potential, and electrical field times distance is going to be electrical potential. And in particular, here's our first concept here. If I have 2 metal plates that are charged up plus and minus, so that a constant electric field exists between them. Notice the direction of the electric field, it goes from plus to minus like you would expect. And if I now start at one side, well, we start all the way over here at point A, and I go all the way to point B, and what I'd like to know is what is the change in electric potential between point A and point B. Then I can ask how much work has to be done, how much work is done as we move in this direction. What is work is done on a positive charge? And so if I think about work being done as work equals force times distance times the cosine of the angle between, and the force is equal to charge times field, and the direction that I'm moving is from A to B. The field is pointing that way, so the angle between the two is 180 degrees, and the cosine of 180 degrees is -1. The work that's done. Try closing the door.
Okay, what is force equal to again?
Force is charge times field.
Right. Okay.
Yeah, like it has been. And so the work that's done is negative QED. And as a result of that work, we go up in potential energy. The potential energy is the opposite of the work done. And therefore, the change of potential energy is positive Q times E times D. And this right here is my delta V. Well, if you compare these two, you can see that the change in potential that we get is equal to field times distance. But we're going to insert the negative sign because the field points in the opposite direction of the distance that is traveled. In other words, as I go up field lines, I'm going to go up in electrical potential. So this is going to be our first major equation right here. And then yesterday, towards the end of class, we talked about the potential caused by a single point charge, or the potential of a single charge. And what I argued there was that we needed a little bit of calculus to make it happen, but we could show that the potential for a single point charge is going to be kq divided by the radius, the distance that we are from that charge. So if this is my charge and I'm at point A right here, then the distance from the charge to point A is r, and the amount of potential created by that charge is going to be kq over r. Here we're going to actually take into account sign. So positive charges are going to have positive potential, and negative charges will have negative potential. And if we're thinking about electrical potential as being like height, then you can draw a picture for yourself. This positive charge right here in a sort of 3D picture, if this is my positive charge, is going to have greater potential the closer you are to it, and then as you get out away from it, it's going to have negative potential. So it's sort of like a volcano or something like that. If I place another positive charge near it, that other positive charge is going to have potential energy that will push it out away. And that's exactly what we expect, right? We expect positive charges to be pushed out away from other positive charges. So what do we need to be able to do here? Well, we basically need to be able to relate several quantities. We need to be able to relate field to potential, and we're going to do that primarily through delta V equals negative ED. And we also need to be able to relate potential to energy. And that is delta U, potential energy, equals Q times delta V. In a lot of ways, we're going to use this we're going to think about this just like you would MGH. So if I have an object that goes higher, its potential energy is going to increase. If I have an object that goes lower, its gravitational potential energy decreases. With electrical potential, it's much the same. If I go up in voltage, a positive charge is going to increase in potential energy. If I go down in voltage, the positive charge will decrease in energy. The one difference is that whereas masses are always positive, charges can be either positive or negative. So every time we deal with a negative charge, we have to reverse our thinking about it. A negative charge that goes up in voltage is going to lose potential energy. And a negative charge that goes down in voltage will increase. Yes?
What does, I didn't try something with one question, but what does Q stand for?
Charge.
Thank you.
Not a dumb question. I recognize that we're doing a lot of sort of abstract thinking, and then we've got a lot of different terms. So if you have any questions like that, feel free to say something. All right, let's actually take a look at problem number 4 on page 489. And in problem number 4, we have an electron that acquires um, 7.45 times 10 to the minus 16 joules of energy. When it is kinetic energy, when it is accelerated, by an electric field from plate A to plate B. So we have plate A and we have plate B. And let's make, we're not sure which one is plus and which one is minus. The electron is going from plate A to plate B. Can we figure out which one is plus and which one is minus? B is plus and A is minus. Why is that? How do you know that B is plus and A is minus? It's being attracted to a positive charge, so it must be that plate B is positive. We know that the electron has a negative charge. Very good. Okay, so B is positive and A is negative. And what we know is that the electron is gaining as it goes from A to B. It gains kinetic energy of 7.45 times 10 to the minus 16 joules. Okay. So the next question is, what is the voltage difference between the plates? Now what's interesting about this is they don't give us a distance of separation from the plates. And that's okay. We don't need it. We're going to work strictly in energy terms to figure out the voltage difference here. Because we know that the change in potential energy is equal to the charge on the electron times its change in voltage.
Wait, can you scroll over here a minute? I just want to see
Okay. Now, the charge on the electron we know about. The charge on the change in voltage we're trying to find. What about that change in potential energy here? We weren't given a change in potential energy. We were given a change in kinetic energy. Are those two related in some way? Yes, that's exactly right. Whatever kinetic energy was gained, it was gained at the expense of losing potential energy. So I can immediately say that delta U is this right here. Does everybody see that logic? This is the key point in the problem. The rest is just plugging in. Okay, so now we plug in. And the charge on the electron is? Yes, but louder. I don't think Evan can hear you.
1.6
Units? Cool, exactly so. Everybody go ahead and solve for the delta V. Yes. Ah, yes. So the electron's charge is actually negative. That's right. Good. The signs. Yep, exactly. So you have to remember the sign for that. And I was just going to let things spin out, but you caught it.
On our quiz, will we get like negative or the number 1.9, 1.6, or 2, 3, 7, 19?
I'll give you the mass of the electron.
Okay, I found it.
The charge on the electron is a basic thing that you need to know.
Okay. The mass is like, wait, is it 9.11?
I'm saying the negative 30%. No, I'm saying the 30%.
Big electron.
About 10 suns worth of mass.
That would track a lot of things.
Yeah.
What about the value for kinetic?
The value for K.
We give it?
Of course you know it by now because you use it so much.
Like 8.9
Consider the 9. 9E9 is the way I remember it. Okay, what do you get for your delta V? Somebody, anybody? What you got?
4,650?
Sounds about right.
4?
4,650 volts, and that's plus. Let's see if it makes sense that it is plus. Let's go back to our picture. Does it make sense that as I go from A to B that I am increasing in voltage?
Yes.
Why, yes, it does. I'm going from a negative plate to a positive plate, so I should be increasing in voltage. If I had gotten a negative, that would mean that I am decreasing in voltage, and that wouldn't make any sense, right? So that would provide the check for where did I get my sign from. Because if I am going from a negative plate to a positive plate, I have to be going up in voltage. Positive charges produce positive potential. Negative charges produce negative potential.
Okay, and then what was that thing you were saying when,
Right, say again?
I don't know, you were saying something earlier.
I don't know. But let's draw a picture so we can see what's happening here. What's happening here, if I use height as my analogy, is that I can call some place arbitrarily 0, so I'm going to call the minus place at 0 volts. I'm going to say that's right. And the positive one is now at 4,650 volts. And as I go from here to here, my electron, which is negatively charged, is falling up. And that's what negative charges do. They fall up these voltage slopes because they have negative charges. Does that make sense? So one picture that I'm trying to get across to you guys is that positive charges fall down, just like positive masses do, and negative charges fall upwards. Does that help? Now here's an interesting thing that the problem does not ask us, but I want to compare. Suppose I move these two plates apart a little bit. What would change? Yeah.
There need to be an increase in voltage and more power.
As it turns out, no. That's the interesting thing about this, is that there isn't an increase in voltage. Instead, what happens is this. If I pull the plates apart so that they are at a further distance, then the voltage remains the same, but the slope decreases. Just like that. And what is that slope? That slope right here is the electric field between the two plates. The value of the slope is the electric field. How do I know? Because the equation runs delta V equals negative ED, so that if I divide both sides by negative D, neglecting the negative sign here, I get delta V over D, and in my diagram, D is that distance right there, and delta V is the change in voltage right there. That's the slope. So the slope here tells us the value, the magnitude of the electric field between them. If I take the plates apart, then I decrease the electric field so that the electron will take a longer time to get there, but it will still have the exact same amount of energy when it goes. Can you see that?
What if you start to decrease it? So we're saying?
Yeah, same voltage, different slope. So you have a stronger electric field. Any questions about this one? In the spirit of that, I want to talk about a common unit of energy that you will see. You'll notice that we have delta U equals Q delta V, right? So if I simply plug in 1 electron's worth of charge, which has an elementary charge E, into 1 volt right there, what I get is a unit of energy called an electron volt. And it literally means the charge of 1 electron times 1 volt. How much is an electron volt? Well, I can plug in 1.602 times 10 to the minus 19th coulombs times 1 joule per coulomb gives me 1.602 times 10 to the minus 19 joules. So that one electron volt is simply a very small number, actually E's worth of joules. You say, well, why would we use electron volts? Because it's actually really convenient. If I have a power supply that's 200 volts, and I turn an electron loose at that power supply, and I ask how much energy does the electron have when it hits the other side, the answer is easy, 200 electrons. So it's a very convenient way of accounting for energy in when you're dealing with elementary particles like that. In fact, the people that run particle accelerators are going to be measuring the energies of those particles in kilo-electron volts or tens or hundreds of kilo-electron volts, maybe even a mega-electron volt. So in that spirit, let's take a look at number 11 on that same page. What is the speed of an electron with a kinetic energy of, well, here we'll do part B, 3.2 kilo-electron volts, or keV. And so what are we told here? The electron has kinetic energy, or 1/2 mv squared, of 3.2 times 10 to the third kilo-electron volts, just like so. And now we just need some numbers. We need the mass of the electron, which is 9.11 times 10 to the minus 31st kilograms. And we need to know that an electron volt, as we just saw, is 1.602 times 10 to the minus 19 joules. And from here, it's just a matter of solving for V. First, V squared should be equal to all of those things multiplied and divided. So we'll start here, 3.2 times 10 to the third times 1.602 times 10 to the minus 19. It's a lot of decimal places. Times 2 divided by 9.11 times 10 to the negative 31st. Notice, interestingly, that we had really, really small numbers for our energy over here. But because the mass of the electron is so very, very much smaller, we're going to end up with an actual large value for V squared. It's going to be 1.1 times 10 to the something. I'm not even going to bother. Well, should I? 3, 6, 9, 12, 15. Meters squared per second squared. So that my velocity now, I knew that would happen, is going to be 3.35 times 10 to the 7th meters per second. Interestingly, the speed of the electron is limited by the universal speed limit. What's the fastest anything can possibly go? Speed of light, which is 3 times 10 to the 8th meters per second. So we're getting close. We're about 10% of the speed of light now. You say, well, what does that mean? Does that mean I just can't put any more energy into the electron? No, actually, what it means is, as we get close to the speed of light, we discover that the formula 1/2 mv squared is not exact, but an approximation of the kinetic energy of particles. Yeah.
Then they need more energy, like go per.
To go faster. That's exactly it. That's exactly what happens. Questions? Yes, Peter.
Still don't get what that K stands for.
Here?
Yeah.
Kinetic energy. In the problem it says kinetic energy.
So it's just, oh, okay, I get it.
Good. Any other questions? Okay. Let's take a look now at one more problem. I want to look at number 24 on that page. Consider a point which is 72 centimeters north of a negative 3.8 microcoulomb point charge. And a point B, which is 88 centimeters west. And now what they want us to determine is the difference in potentials between these. And they also want us to determine the difference in fields. Okay. What I like about this problem is that it's going to illustrate the mathematical difference between potentials and fields. Potentials are going to be scalar quantities, so we don't have to worry about direction. Yes. Fields are vector quantities, so we're going to have to worry about direction. Now, in this particular problem, the directions aren't too hard. But still, with a field, we're going to have to be concerned with magnitude and direction. With potential, we only care about the magnitude, the size of it. So here at point A, we're going to, because this is a single charge generating this whole thing, we're going to say that the voltage at point A is equal to K, the Coulomb's law constant, times Q, divided by the distance between. Oh, can I help you? An iPad? What color case? I'm sorry. Our first casualty. Probably not the first. Has anybody had a shattered screen yet?
I've seen them. I left mine here over a 4-day weekend.
Did it get lifted?
Yeah.
You got it, yeah. Yeah. It is. You know, it's interesting. Let me turn this off for a second. So what we're going to do is just simply compute the potential here, and subtract, and that's it. So maybe we can divide this up. This half of the class, I'd like for you guys to compute VA using the formula. That half of the class, compute VB. Go. Keep in mind that it's a negative charge. Don't forget that we have to deal in meters and not centimeters. you end up with a fairly horrendously large voltage, right? How about for VB? What do you got, Lindsay? Okay, round that appropriately for us. Sorry, I didn't hear the last words. 800, yeah. Okay. What does this mean? First of all, does it make sense that this one is larger in magnitude than that one? Yes, why? Point B is further. That's right. Point A is closer. Point B is further. Okay. Does it make sense that both of them are negative? Yes, because negative charges produce negative potential, right? And so now, for part A, VBA is simply VB minus VA, or in other words, negative 38,800 minus negative 47,500. And when the dust settles, you end up with positive 8,700 volts. Check that. 5, 7, yeah, that's right. What does this mean? This means that as I travel from point A to point B, by whatever path, that's a very interesting thing about this, that it doesn't matter if I go around, or if I go in curly Q's and then straight there, or if I just cut across, I am going to go up in potential by 3,800 volts. That's much like it works with gravity, right? If I have 2 points, and one of them is 3,800 meters higher than the other, then if I go from here to here by any path whatsoever, I am changing in elevation by 3,800 meters. So we have the idea of path independence. Voltage does not care about path. What path you take to get there. That's one of the major reasons that we prefer using voltage over electric field. With electric field, I got to worry about the field at every point along the path. Okay, well, what about the delta E then? Well, we know how this goes. We know that field has a magnitude of K, Q over R squared. And so I can get the magnitude of the field at A and the magnitude of the field at B. Same sides, do that. Find the field at A and the field at B. Go. And what value did you get for the field? You got it, Blake?
Negative 65,932.2 feet.
How about 66,000? Rounded appropriately. However, I am not going to include your negative sign, and there's a reason for that. Our formula finds the magnitude of the field, but to get the direction of the field, I have to use the idea that field goes into negative charges and out away from positive charges. Yes, that's right. So I'm going to have to go back here and say, all right, this is a negative charge, so at point A, the field is going to point that way, towards the negative charge, which means that my field is actually 0 in the x direction and negative 66,000 in the y direction, like so. So this is an additional complication for field that we did not have with our potentials, with our scalar potential, right? We have to consider direction. We have to do that by what we know about positive and negative charges.
Question.
Yes.
What happens if it were just like a normal angle?
What's that?
What would happen if it was like an angle?
Then we would have to do components.
Would it give you the angle?
Or they give you the information you need to find it. Yeah. Okay, what about the magnitude of B? James, what do you have? 44,000. It's newtons per coulomb. Yeah, not nanocoulombs. That would be charge. That would be a very small charge. And what about direction? Well, I go back to my diagram and I say point B is here, so that my field is going to be in the positive x direction. And I have to do it from the diagram. So my field at B is going to be 44,000, 0 newtons per coulomb. And now when I find the difference in fields, EB minus EA, then I subtract them like vectors. This one minus that one. So that, importantly, I do not end up subtracting the 44,000 from the 66,000 at any time. Why not? Because they are in different directions, x and y. And this is my net field, the difference in fields. The difference in fields doesn't have a lot of significance, physical significance. Just describes how the field changes. To get from this to this, I have to change the field like that. How are we doing? I think we're all on daylight savings time. Did you feel it this morning trying to get up? Oh my God.
I sleep an hour later now. I can't fall asleep.
Yeah. Okay. Let's do one more. I want to take a look at number 22. And in number 22, we have 2 point charges that are 3 microcoulombs and negative 2 microcoulombs, and they're placed 5 centimeters apart on the x-axis. Do I know which one is to the left or to the right? No. So what do? Panic. Yep. Oh, pick one. Oh, good. Okay. For a second there, I thought I couldn't do the problem. Okay. I also don't have coordinates. Definitely panic. Which I do. What's the smartest coordinate choice there?
0.
0 where?
Right in the middle. I mean, no.
Could.
No, all negative, yeah.
I kind of like 0 here.
Yeah, I like that too.
But I could. If I did 0 in the middle, what would my coordinates be for the 2 charges?
It, weight, it'd be 2.5. Yeah.
And?
2.5 negative.
Negative 2. Exactly so. There's no wrong answer to our coordinates here, but this is probably the most convenient. And now they want to know, at what points is the electric field 0? And at what points is the electric potential equal to 0? Yes.
Can you use proportions to find this or not?
Well, let's answer that question retrospectively. Let's set up the equations and then see if proportions would have worked.
So, yeah.
Okay. So let's start with electric field. I don't know what point we're talking about, so I'm going to go to some point x. And I don't know if x is over here, or maybe it's in between, or maybe it's back over here. I'll find out from the equation. If x is between 0 and 5, then it's between. If it's bigger than 5 over here, if it's less than 0, then over here. And I'm going to say that the total electric field generated by this is going to be equal to. Now, let's see here. If this is x, then my distance to x is 5 minus x. And if this is x, my distance to x here is x itself. But I have a problem. I've got to figure out direction. So let's assume for just a moment that x is bigger than 5, that x is over here somewhere. And if that's so, then is this guy going to be positive or negative? Well, this is a positive charge, and it puts out electric field in this direction, like so, out away from itself, right? So therefore, on this side of 5, this is positive. Whereas the negative charge sucks in field lines towards itself, so that on this side of 5, this guy is negative, just like that. Does everybody see how I did that? And now I set all this equal to 0. And when I set it equal to 0, then I think I can probably simplify. I'm going to divide both sides by k, so I don't have to worry about that. And I'm going to divide both sides by 10 to the minus 6, so I don't have to worry about that. And I get this equation, 3 over 5 minus x squared plus 2 over x squared is equal to 0. Probably the best way to solve this equation is by calculator. If you want to do a little bit of cross multiplying, you could do that. But before we get too involved with it, I just want to examine that equation and observe something. That equation can't possibly have a solution, and Catherine's going to tell us why. This sign right here?
No, the 2x, 2 over.
Oh! Ha! Because I wasn't paying attention, because daylight savings time. And now our equation could possibly have a solution, and it probably does. So I could do calculator here. If I felt like not doing calculator though, I could probably take a square root of both sides, couldn't I? And if I do that, bless you. And when I do, I get two different equations, accounting for the plus or minus. And the two different equations now are going to give me two different solutions. And I'm willing to bet that one of them is on that side of 5, the other one's on that side of 5. Oh, that's 0. Does that make sense? Okay, so much for that. Actually, let's, do we have time? We have quite a time to get into numbers, yeah.
This is one way. How many points off would you get once it starts to go through? You couldn't do that part. Is that?
How about, let's ask a different and better question. What would it take to learn how to do that part?
Algebra 1 and algebra 2.
Okay. All right. So you look at that and you say, I want to be able to do that, right? Tommy looks at some guy pulling a skater trick. He says, I want to be able to do this. Right? Yeah.
Well, electric potential is just
Okay, that's this stuff.
Okay, so what is a volt? That's what she asks. Mathematically, a volt is a joule per coulomb. It's the amount of potential energy stored per coulomb. So if I get a 9-volt battery, that's telling me if I stick a coulomb of charge at the plus side, and it travels all the way to minus side, it will have 9 joules of energy by the time it gets there. How much energy is stored. And so we use height as an analogy here. it's like having it's like having a 40 meter water. So if you've got a kilogram of mass, then the potential energy, kilogram of 0.9 or joule of energy is 9 joules of energy. And you release that energy by letting it go.
Yeah, not that,
There were some more things I wanted to say about this problem. I think what I'm going to do is to work this problem in completeness in seventh period so that you can see the whole thing. Because here's the important thing. The places where the electric field is equal to 0 will not be the places where the voltage is equal to 0. In fact, there is a relationship between them. Calc students, you can probably figure it out by recognizing that electric field is the derivative of the voltage.
Where's the homework?